people think of semen, they usually think of sperm. But sperm cells make up only a small fraction of semen's volume, typically around 2 to 5%. So what makes up the other 95% or more? That's where things get interesting. Semen is not just a carrier for sperm. It's a complex, carefully formulated, water-based biological fluid designed to nourish, protect, and transport them. So where does semen come from? It is produced by 3 main glands that work together like a biological manufacturing system. First, the seminal vesicles. These 2 small glands, located behind the bladder, contribute about 60 to 70% of the semen's volume. Second, the prostate gland. This gland adds roughly 20 to 30% of the total volume and provides substances that help sperm function effectively. Third, the bulbourethral glands, also known as Cowper's glands. They contribute only a small amount, typically less than 5%, but serve an important role that we'll come back to shortly. Each gland contributes a different set of ingredients, and when you look at what's actually being added, semen stops looking like a simple fluid and starts looking more like a highly specialized biological delivery system.
Station 1. The seminal vesicles. The seminal vesicles produce the largest portion of semen, about 60 to 70% of the total volume. At its core, this fluid is mostly water, acting as the primary highway for transport. But dissolved within that water is a thick, slightly sticky mix rich in fructose, a simple sugar. Why sugar? Because sperm need energy. Once ejaculated, they must power an extraordinary journey, and fructose serves as one of their primary fuel sources. In fact, fructose levels are sometimes measured during semen analysis. Very low levels can be a clue that the seminal vesicles aren't functioning properly. The seminal vesicles also contribute bicarbonate. This is important because the vaginal environment is naturally acidic, with a pH typically around 3.8 to 4.5. That acidity helps protect against infection, but it's also hostile to sperm. Bicarbonate helps buffer that acidity, creating a more favorable environment for sperm survival. Think of it as nature's own antacid, giving sperm a better chance to continue their journey. The seminal vesicles also produce clotting proteins. Immediately after ejaculation, these proteins cause the semen to rapidly form a soft, gel-like clot. This temporary structure helps keep the semen securely near the cervix, rather than allowing it to leak out. Additionally, they secrete prostaglandins. Despite their name, which makes them sound like they belong to the prostate, these hormone-like molecules are mainly produced right here in the seminal vesicles. They help trigger tiny muscular contractions in the female reproductive tract, essentially helping pull the sperm along on their journey. Station 2. The prostate gland.
The prostate contributes roughly 20 to 30% of semen volume. Like the seminal vesicles, the prostate utilizes water as its base, but it infuses this water with a totally different chemical profile. One of its most remarkable contributions is zinc. Prostatic fluid contains zinc concentrations far higher than those found in blood. Zinc plays important roles in sperm stability, membrane function, and the protection of genetic material. Research has linked zinc deficiency with reduced semen quality and impaired male reproductive function. But the prostate's most famous contribution may be a group of enzymes, including PSA, or prostate-specific antigen. This enzyme performs a fascinating task. Remember that temporary gel fortress built by the seminal vesicles? PSA is the key that opens the gates. Over the course of 15 to 30 minutes, this enzyme breaks down the gel clot, liquefying the semen and freeing the sperm to finally begin swimming freely. It's almost as if semen builds a temporary fortress and then opens the gates at exactly the right moment. The prostate also releases microscopic particles called prostosomes. These tiny membrane-bound vesicles are typically around 40 to 500 nanometers in size and carry proteins, lipids, and genetic material. Scientists are still investigating their exact functions, but evidence suggests they interact directly with sperm cells, helping regulate motility, protection, and fertilization-related processes. Station 3, the Cowper's glands. Finally, we arrive at the bulbourethral glands, better known as Cowper's glands. Unlike the other stations, these small glands don't contribute much to the final ejaculate pool. Instead, they produce pre-ejaculatory fluid, often called pre-cum. Released before ejaculation, this fluid serves as the ultimate cleanup crew. It helps lubricate the urethra and may help neutralize residual acidity left behind by urine, creating a more sperm-friendly passageway. In a sense, it's the cleanup crew that arrives before the main event. Put everything together, and semen turns out to be far more than just sperm. It is, first and foremost, an aquatic ecosystem. It is mostly water, but it is water precisely weaponized with sugars, minerals, proteins, enzymes, signaling molecules, and buffering compounds. The final mixture is slightly alkaline, typically around pH 7.2 to 8.0, helping counteract the acidic environment sperm encounter after ejaculation. A typical ejaculation contains hundreds of millions of sperm cells, yet all those sperm together account for only about 2 to 5% of the total semen volume. The vast majority of what you see is fluid produced by the accessory glands, not sperm themselves. Every ingredient serves a purpose. Every gland contributes something unique. Every single component works as part of a highly coordinated system, each with one goal: giving sperm the best possible chance of creating new life.